Okay, now I want to tell you what the first two of Kepler's three laws are, using the same diagram I've already drawn here. So K1L, that just means Kepler's first law, and we've actually established that each planet's orbit is elliptical, with the sun located at one focus. We can expand that, like the moon's orbit around the Earth is elliptical with the Earth at one focus, same as any satellite orbiting the Earth. Okay, but we'll restrict it to planets for today. Kepler's second law doesn't make too much sense by reading it, but I'm going to draw on this diagram and I'm hoping it makes more sense. So to me, this is really impressive that Kepler was able to come up with this in 1600 just by looking at the position of Mars over decades. Okay, so planets move through their orbits in such a way that they sweep out equal areas in equal times. Okay, so I'm going to modify this diagram here so it makes a bit of sense. I'm going to highlight the planet here when it's close to the sun. I'm just going to give kind of an arbitrary time interval and call it 1 month. So let's say in 1 month, the planet's moved through this much of its orbit. It sweeps out an area if you connect the planet's position to the sun. Okay. We'll call this area 1, A1. Okay, so this is what I mean by sweeps out an area. In 1 month, it sweeps out this much area when connected to the sun. Kepler's law is saying it sweeps out equal areas in equal times. So any 1 month interval in the orbit has to sweep out this much area. Now I'm going to draw something over here. Over here, the planet is much farther away from the sun. So that means when we connect it to the sun, as it moves, we get a lot more area. So for Kepler's second law to hold, it can't go that far. It's not going to go nearly as far as on the other side. So I'm just eyeballing this, but I'm hoping it looks pretty okay. So I connect these two, this really long, kind of rounded triangle should have the same area as this one. So that's an illustration of Kepler's second law. If it moves this far in 1 month, we get this chunk of the orbit. It's got to be equal anywhere on the path. I've chosen over here to exaggerate the effect. Okay? And I think you can tell now by looking, it travels much farther when it's closer to the sun than it is when it's far from the sun. And this is true that in an orbit, the speed's not always the same. Things are moving faster when they're close to what they're orbiting. Again, Earth's orbit is so close to circular, this has not much effect on us, but there are certainly other planets and moons where this would be more prevalent.